Welcome! This video will walk you through the derivation of the exponential generating functions for Bernoulli numbers and Bernoulli polynomials. We begin by recalling the Bernoulli numbers, a special sequence of rational numbers. The first few, following the convention where the first is b sub 0, are displayed on screen. There is no simple explicit formula for these numbers, but they can be defined by a recursive formula. For the nth Bernoulli number b sub n, the formula is shown here. From this recursive formula, we can derive a key identity that we will need later. Let's derive it for a specific case to see how it works, using b sub 3. Starting with the recursive formula for n equals 3, we see the expression on screen. Now, let's unpack this sum term by term. The expanded form is displayed. Calculating the binomial coefficients, we have 3 choose 0 equals 1, 3 choose 1 equals 3, and 3 choose 2 equals 3. And substituting the known Bernoulli numbers, b sub 0 equals 1, b sub 1 equals negative 1/2, and b sub 2 equals 1/6, we get the substituted expression shown. Now we perform the arithmetic within the brackets. Each fraction is calculated step by step on screen. So the sum inside the brackets gives us 1/4 plus negative 1/2 plus 1/4, which equals 0. Therefore, b sub 3 equals negative 0, which is 0. This confirms that b sub 3 equals 0, which matches our initial list. Now, let's perform the clever step. We multiply both sides of the original recursive equation for b sub 3 by the binomial coefficient 4 choose 3. First, calculate 4 choose 3. We have 4 factorial over 3 factorial times 1 factorial, which simplifies to 4. Multiplying both sides of the recursive equation is shown here. Since b sub 3 equals 0, the left side is 4 times 0 equals 0. Let's focus on simplifying the right side. We substitute the values of the binomial coefficients. We can simplify this expression. Notice that the 4 outside multiplies each term in the sum. Also, the denominators 4, 3, 2 can be absorbed into the binomial coefficients. The detailed simplification is written out on screen. Now we cancel the terms systematically. After cancellation, we get 1 times 1 plus 4 times negative 1/2 plus 2 times 3 times 1/6, which simplifies to 1 minus 2 plus 1, giving us 0. Now, let's rewrite this result in terms of binomial coefficients. The terms we got were 1, negative 2, and 1. Notice that 1 equals 4 choose 0 times b sub 0, negative 2 equals 4 choose 1 times b sub 1, and 1 equals 4 choose 2 times b sub 2. Let's verify this. 4 choose 0 times b sub 0 equals 1 times 1 equals 1. 4 choose 1 times b sub 1 equals 4 times negative 1/2 equals negative 2. 4 choose 2 times b sub 2 equals 6 times 1/6 equals 1. These verifications are shown. Our equation was 0 equals negative the quantity 1 minus 2 plus 1. Distributing the negative sign and moving everything to the left side, we get the identity displayed on screen. This is a specific case of the general identity we need, which is shown here. For n equals 3, this is the sum from k equals 0 to 3 of 4 choose k times b sub k equals 0, which we have just verified. Our goal is to show that the Bernoulli numbers are the coefficients in the Maclaurin series of the function f of x equals x over the quantity e to the x minus 1. This function is called the exponential generating function for the Bernoulli numbers. To derive this, we start by considering the product of the Maclaurin series for e to the x and an unknown function f of x. The Maclaurin series for e to the x is displayed on screen. The general Maclaurin series for a function is also shown. We multiply these two series using the Cauchy product. This involves creating a two-dimensional array where each term of the first series multiplies every term of the second series, and then summing the results along diagonals where the sum of the exponents of x is constant. Let's construct part of this array. We'll write the terms of e to the x horizontally and the terms of f of x vertically. The product f of x times e to the x will be the sum of all entries in this infinite array. The first few diagonals are shown. For diagonal 1, we have the power of x to the first. For diagonal 2, we have the power of x squared with its contributing terms. For diagonal 3, x cubed with all its terms. And for diagonal 4, x to the fourth with its complete set of terms. Now we sum the terms along each diagonal. For each diagonal corresponding to power x to the n, we factor out x to the n. The complete series is displayed on screen. The next clever step is to multiply and divide each grouped term, the coefficient of x to the n, by n factorial. This is the creative form of 1. The transformed series is shown. Now we distribute the n factorial into the numerator of each term within the brackets. Let's do this for the x to the fourth term as an example. The coefficient for x to the fourth is written out in detail, showing how 4 factorial multiplies each fraction. Simplifying each term by canceling factorials gives us the cleaner form displayed. Notice that these fractions are binomial coefficients. 4 factorial over 0 factorial times 4 factorial equals 4, choose 0. 4 factorial over 1 factorial times 3 factorial equals 4, choose 1. 4 factorial over 2 factorial times 2 factorial equals 4, choose 2. 4 factorial over 3 factorial times 1 factorial equals 4, choose 3. So, the x to the fourth term becomes 1 over 4 factorial times the bracketed sum of binomial coefficients times the derivatives, as shown. Applying the same process to all terms, the full product is displayed on screen with all terms written using binomial coefficients. Now we make a crucial observation. Recall the identity we derived earlier. The sum from k equals 0 to n of n plus 1 choose k times b sub k equals 0. If we set the derivatives of our function f at 0 to be the Bernoulli numbers, that is, the nth derivative of f at 0 equals b sub n, then the expressions in the brackets become very similar to this identity. For example, look at the coefficient of x cubed, which is 1 over 3 factorial times the bracketed sum shown. Our identity for n equals 2 is the sum from k equals 0 to 2 of 3 choose k times b sub k equals 0, which is exactly 3 choose 0 times b sub 0, plus 3 choose 1 times b sub 1, plus 3 choose 2 times b sub 2 equals 0. So, this entire term vanishes. Similarly, for x to the fourth, the coefficient involves the sum shown on screen. Our identity for n equals 3 tells us this sum equals 0, so this term also vanishes. In fact, for all n greater than or equal to 1, the coefficient of x to the n will vanish if the nth derivative of f at 0 equals b sub n, thanks to our identity. The only terms that remain are the very first term, which is b sub 0, and the term from the first diagonal, which is b sub 0 times x. Since b sub 0 equals 1, the entire product simplifies dramatically to 1 plus x. But wait, we defined f of x as our unknown function whose derivatives at 0 are the Bernoulli numbers. So, we have f of x times e to the x equals f of x plus x, which can be written as shown. Now we can solve this equation for f of x. Subtracting f of x from both sides gives us f of x times e to the x minus f of x equals x. Factoring out f of x on the left gives us f of x times the quantity e to the x minus 1 equals x. Finally, dividing both sides by the quantity e to the x minus 1 gives us f of x equals x over the quantity e to the x minus 1. And we assumed that the Maclaurin series of this function has coefficients equal to the Bernoulli numbers. The nth derivative of f at 0 equals b sub n. Therefore, we have derived the exponential generating function for the Bernoulli numbers. The complete series is displayed on screen. Let's verify this for b sub 0 and b sub 1. To find f of 0, we need to evaluate x over the quantity e to the x minus 1 at x equals 0. We get 0 over 0, an indeterminate form. We use L'Hopital's rule. Taking the limit as x approaches 0, we differentiate the numerator and denominator. The calculation is shown, giving us the limit of 1 over e to the x, which, as x approaches 0, equals 1 over 1 equals 1. This matches b sub 0 equals 1. Now, let's find f prime of 0 to see if it equals b sub 1 equals negative 1/2. We need the derivative of f of x equals x over the quantity e to the x minus 1. Using the quotient rule, the derivative is calculated and displayed. Now, evaluating at x equals 0, we substitute and get e to the 0 minus 1 minus 0 times e to the 0 all over the quantity e to the 0 minus 1 squared. This simplifies to 1 minus 1 minus 0 over the quantity 1 minus 1 squared, which is 0 over 0. Again, an indeterminate form. We apply L'Hopital's rule to f prime of x itself. The limit expression is shown on screen. We differentiate the numerator and denominator. The derivative of the numerator, e to the x minus 1 minus x times e to the x, is calculated step by step, giving us negative x times e to the x. The derivative of the denominator, the quantity e to the x minus 1 squared, equals 2 times the quantity e to the x minus 1 times e to the x, which is 2 times e to the x times the quantity e to the x minus 1. So the limit becomes the simplified form shown. We still have 0 over 0 as x approaches 0. We apply L'Hopital's rule again. The derivative of the numerator, negative x, is negative 1. The derivative of the new denominator, 2 times the quantity e to the x minus 1, is 2 times e to the x. So, the limit as x approaches 0 of f prime of x equals the limit as x approaches 0 of negative 1 over 2 times e to the x, which equals negative 1 over 2 times 1, which is negative 1/2. This matches b sub 1 equals negative 1/2. The generating function works. Euler generalized this idea by considering the product of our generating function x over the quantity e to the x minus 1 with e to the xt, where t is a new variable. The product is displayed. We know the Maclaurin series for both parts. The series for x over the quantity e to the x minus 1 is shown, and the series for e to the xt is also displayed. We multiply these two series again using the Cauchy product. Let's look at the first few diagonals of the resulting array. For diagonal 1, we have the power of x to the first with its term. For diagonal 2, the power of x squared with its contributing terms. For diagonal 3, x cubed with all its terms displayed. Summing along the diagonals and factoring out the power of x, we get the complete series shown on screen. Again, we multiply and divide the coefficient of x to the n by n factorial. Let's do this for the x cubed term. The detailed calculation is displayed, showing how 3 factorial is distributed. The fractions become binomial coefficients as shown. 3 factorial over 0 factorial times 3 factorial equals 3 choose 0. 3 factorial over 1 factorial times 2 factorial equals 3 choose 1. 3 factorial over 2 factorial times 1 factorial equals 3 choose 2. Applying this pattern to all terms, we get the exponential generating function for the Bernoulli polynomials displayed on screen, where the nth Bernoulli polynomial, b sub n of t, is defined by the formula shown. Let's compute the first few Bernoulli polynomials. For n equals 0, the calculation is shown step by step, giving us b sub 0 of t equals 1. For n equals 1, the full expansion is displayed, showing b sub 1 of t equals the sum from k equals 0 to 1 of 1 choose k times b sub k times t to the 1 minus k, which expands and simplifies to t minus 1/2. For n equals 2, the complete calculation is shown with all terms. b sub 2 of t equals the sum from k equals 0 to 2 of 2 choose k times b sub k times t to the 2 minus k, which expands to the expression shown, simplifying to t squared minus t plus 1/6. For n equals 3, the full expansion is displayed. b sub 3 of t equals the sum from k equals 0 to 3 of 3 choose k times b sub k times t to the 3 minus k. All terms are calculated and shown, giving us t cubed minus 3/2 times t squared plus 1/2 times t. So we have the four Bernoulli polynomials displayed. b sub 0 of t equals 1, b sub 1 of t equals t minus 1/2, b sub 2 of t equals t squared minus t plus 1/6, and b sub 3 of t equals t cubed minus 3/2 times t squared plus 1/2 times t. Notice that if we set t equals 0 in the generating function, x times e to the xt over the quantity e to the x minus 1, it reduces to x over the quantity e to the x minus 1, the generating function for the Bernoulli numbers. Correspondingly, if we set t equals 0 in the Bernoulli polynomials, we get the Bernoulli numbers. b sub n of 0 equals b sub n. This concludes the derivation of the exponential generating functions for both the Bernoulli numbers and the Bernoulli polynomials.